Hey everybody. So we just learned the definition of a logarithm, and we should be able to evaluate logarithms, right? If I asked you what's the log base 2 of 8, you would say 3 because 2 to the third is 8. But what we're going to shift today is we're going to switch from just thinking about logarithms of specific values. Let's look at logarithms as functions, right? So if I say the log base 2 of x, y equals the log base 2 of x, f of x equals the log base 2 of x. Then we can switch to anything, right? So some nice x values might be, like I said, 8, because the log base 2 of 8 is 3. Or if I said x is 2, the log base 2 of 2, well, 2 to the what power is 2? 1, right? So we can think about them as functions. And if we think about them as functions, we should ask ourselves, well, I wonder what their graphs look like. So today's goal is that I give you any logarithmic function and you can come up with the graph. Now, before we get to the graphs of actual logarithmic functions, let's do a little bit of review from earlier in the year when we talked about inverses. Okay? 3 things that we know about inverses. Number 1, is that when we look at inverses, we switch the x's and the y's. So for example, if the point 1, 2 is on f, the point 2, 1 is on f inverse, right? We switch x's and y's, and you might recall that's how we found the equation of an inverse. So if I said, what's the inverse of y equals 2x minus 1? Do you remember how we switched and we said x equals 2y minus 1, and then we solved? And this is the inverse of that, all right? So we had that switching x and y stuff. Now, what happens to the graph, okay, if we take every point on a curve and we switch their x's and y's? Well, their graphs are reflections in the line y equals x. Okay, maybe you can picture that, okay, how when we looked at we checked to make sure they're inverses by graphing both of them and checking, did it really look like they're reflections over the line y equals x? The last thing, number 3, about inverses is when you substitute the inverse into the original function. You put f inverse into f, what happens? They cancel each other out and they just give you x. Okay. For example, if f of x is x squared and f inverse of x is the square root of x. Now this is just a quick note here. This is only for x's that are greater than or equal to 0. Okay. Okay. What happens when I put f inverse into f? Oh, missing a parenthesis. It's f of the square root of x. And what happens? Well, I have to put that into f. So I'm going to take the square root of x and square it, and I get just x. They cancel each other out, right? What's the inverse of adding 1? Subtracting 1, right? Inverses cancel each other out. And same with the other way around. Also, if I put f into f inverse, they cancel each other out, leaving x. If I did this stuff over here, okay, and I just switched the order, the same thing would happen. So those are reminders of inverses. Okay? X's and y's switch. They're reflections over the line y equals x. And when you substitute a function into its inverse, they cancel each other out, giving you x. Now, why am I talking about that? Well, let's look at these two functions. F of x equals the log base 2 of x, and f of x equals 2 to the x. Okay. Can we show that these two functions are inverses? Well, what I'm going to do is I'm just going to call that f inverse, all right, instead, so we know which is which. So of these 3 things about inverse, which one of them do we use to prove functions are inverses? And it's number 3. Okay. Okay, number 3, where we substitute one into the other and see them cancel out, is what we use to prove that they're inverses. So let's do that. Let's first look at f of f inverse of x. Let's put this 1 over here into that function. So that becomes f of, what's f inverse? 2 to the x. Now I have to put 2 to the x into the f function. So this is the log base 2 of 2 to the x. Now, what do I do with that? Well, this is a logarithm. How do we evaluate logarithms? Okay, I want to know what this is equal to. Well, remember, we think about them as exponentials. What question would I have to ask myself? I'll do a little work on the side over here. 2 to the what power? So 2 to the what power equals 2 to the x. And the answer to that is, what's the question mark have to be? It has to be x. So this is really equal to x. So when we put 2 to the x into the log base 2 of x, they cancel each other out. Okay. Awesome. Now, we do have to show the other way as well. Let's look at f inverse of f of x. This is f inverse of f of x is the log base 2 of x. So now we're going to put the log base 2 of x into that function. So it's 2 to the log base 2 of x. Now, what happens with that? Well, this is an exponential. I wonder what would happen if I rewrote it as a logarithm. So let me do a little work on the side here thinking about this. The log base, what's the base of our exponential? 2 of what equals what? Well, remember, okay, that the exponent always goes over here. Okay? We would write this as the log base 2 of what number equals the log base 2 of x. And what's that question mark have to be? It has to be x, doesn't it? So this is also x. Okay? And we just proved that these two functions are inverse. F of x equals the log base 2 of x and f of x equals 2 to the x are inverses. One of them is a logarithm base 2 and the other one's the exponential base 2. And we see that they're inverses. Would this change if I changed the base? Or would this whole thing here still hold true? Like, what if I switch this to be the log base b of x, and this was just b to the x? Wouldn't the results be the same? Isn't the log base b to the x still x? And over here, I mean, everything would still be true, wouldn't it? Okay. So a big takeaway from this is that logarithmic functions and exponential functions with the same bases are, what are they? They're inverses. So, my next example here is to graph f of x equals log base 3 of x. Well, how are we going to do that? Okay. What does this have to do with this statement right here? Well, let's go back to this. What do we know about inverses? We can find inverses by switching x's and y's. Okay. They're reflections in the line y equals x. So here's what I'm going to do. If I want to graph the log f of x equals the log base 3 of x, I first am going to identify its inverse. Logarithms and exponentials with the same base are inverses. So what's the inverse of y equals the log base 3 of x? It's y equals 3 to the x. Can we graph points on y equals 3 to the x? I hope so, right? We've done this. We've been working on this. What are points on y equals 3 to the x? 1/9, 1/3, 1, 3, 9. Let's graph that. -2, 1/9, 1/3, 1, 3, 9. Okay. That's y equals 3 to the x. Now that I know that, what points are on y equals the log base 3 of x? Well, what do we do with points, okay, to get the points on the inverse? We switch the x's and y's. So -2 1/9 becomes 1/9 -2. -1 1/3 becomes 1/3 -1. Then we have 1 0, 3 1, and 9 2. Let's graph those. 1/9 -1. 1/9 -2, 1/3 -1, 1 0, 3 1, 9 2. Look at that. That's not too bad. Let me draw the graph. I hope you just caught me in a mistake. Hey, what mistake did I just make? Hopefully you're saying, should this graph cross the y-axis? If 3 to the x had a horizontal asymptote of y equals 0, what type of asymptote would its inverse have? Well, y equals 0 would become x equals 0. Okay. We have a vertical asymptote there. This graph needs to look like that. Okay. There we go. This is the method that you want to use for graphing logarithms. Because I'm telling you what, if you would have just done what we normally do, right? If you'd have just picked those x values, like I did over here with the exponentials, and you said, okay, what is the log base 3 of -2? Log base 3 of -2. 3 to the what power is -2? Wait, actually I can't do that, can I? And I can't do that, and I can't do that. Log base 3 of 1. What is the log base 3 of 1? 3 to the what power is 1? Okay, that's 0. So I did get that same point, right? It's there and it's there. Okay, then I'd go to 2. All right, log base 3 of 2. 3 to the what power is 2? I don't know, it's something between 0 and 1. I don't have a good point, right? So instead of just picking x values in some sort of pattern and trying to find the y values, it's much easier, okay, to work backwards and start with those nice y values by taking the points on its inverse, the exponential, and then just flipping them. I should also mention this, I haven't mentioned this yet. Hey, we talked about it before. Remember how the inverses should be reflections over the line y equals x? Are they? Absolutely. Yeah, looks good. Okay. Let's try another one. Okay. Let's graph f of x equals the log base 1/2 of x. So again, my process is first, identify this function's inverse. What's the inverse of y equals a log base 1/2 of x? It's y equals 1/2 to the x. So what are those points? There they are. This is exponential decay, isn't it? Can you picture what the graph of the logarithm is going to look like? And can you picture what's this going to look like if we reflect it over the line y equals x? Well, maybe you can picture it. I hope you can. What color should I use here, folks? All right, we'll go to blue. Okay. I think I did that backwards there, didn't I? No, I did it the same. Okay. So let's graph y equals the log base 1/2 of x now. Okay. Well, what do we do with these points over here? We just take the x's and y's and switch them. There we go, and let's graph those. Now, we still will have a vertical asymptote at x equals 0 again. Exponential decay still has a horizontal asymptote of y equals 0, so it still will become a vertical asymptote of x equals 0. So I'll graph it, and it looks something like that. Okay, maybe that's what you pictured. Are these still reflections over the line y equals x? Yes, they are. Cool. So let's make some generalizations here. If I have the log base b of x, what's its domain? Okay, let's look at both of these examples here. Okay, what x values did we graph? What's in the domain of the log base 3 of x? It was x's that are greater than 0. Okay. How about this one? What's in the domain of the log base 1/2 of x? What x's did we graph? X's that are greater than 0. So it doesn't matter what the base is. The domain is 0 exclusive to infinity. How about the range? What y values did we graph on this logarithm? This arrow is going down forever over here, isn't it? So it's negative infinity, and how far does this arrow go up over here? Well, it just keeps going up, doesn't it? It's going to go up forever. It's negative infinity to infinity. Same thing here. This is going to go down to the right forever to infinity, and this is going to go up forever towards infinity. The range, no matter the base, is negative infinity to infinity. But do notice when the base is greater than 1, and if the base is between 0 and 1, the graphs will look different. That's because their exponential graphs look different. Okay? If the base of an exponential is greater than 1, it's exponential growth. Okay? So what does the graph look like, okay, if we reflect that over the line y equals x? Okay? The graph is going to look something like that. That's exponential growth reflected over the line y equals x. Okay. Notice this graph is increasing, isn't it? Now, if an exponential has a base that's between 0 and 1, we know it's exponential decay. And what did it look like when we reflected over an exponential decay function over the line y equals x? It looked a lot different, didn't it? It looked more like this instead, right? Exponential decay reflected over the line y equals x. Okay. Looks something like that, where this function is decreasing. Let me just do a quick demonstration in GeoGebra, not GeoGebra, in Desmos for you. Okay. Let me graph y equals b to the x, make our slider. Okay. We know this well. Bases can't be negative, right? Okay. Let's go with 10. So of course we know we have exponential growth. Okay. And then between 0 and 1, exponential decay. Now let's graph y equals the log base b of x. Here it is in the green. Okay. Notice when it's exponential growth, our logarithm function from left to right is increasing. The bigger b is, the faster it increases. The faster the exponential increases, the slower the logarithm increases. The slower the exponential is growing, okay, so look at the red, the exponential is growing, but it's growing slowly. That's actually making the logarithmic function increase faster. Now what's going to happen when we switch to decay between 0 and 1? Here we are. Red is exponential decay. Our logarithmic function is decreasing. It's going down. The faster the exponential decays, the quicker the logarithmic function starts to level out over here. All right? Oops, what happened there? Of course, the base can't be 0. Hey, did I note that here? This, of course, bases have to be positive. Remember that exponential's bases couldn't be negative. Remember that weird graph with the points and it was kind of alternating all over the place. That's true. All right, so we're just going to look at a few more examples. What am I going to add in here? Well, of course, I'm going to add transformations. And the beautiful thing is, we know our transformation rules always work the same. I have a +1 and I have a ×2. What do we know that multiplying by 2 does to a graph? It vertically stretches it by 2. What do we know adding 1 to a graph does? It moves it up 1. Okay. So if I can just get the parent curve graphed, I can do my transformations. So what is that parent curve? So this is going to take a couple steps here, all right? So our parent curve is just y equals the log base 4 of x, all right? Once I know what that graph looks like, then I can just do my 2 transformations. Now, how do I know what the graph of y equals the log base 4 of x looks like? Well, we use its inverse, just like we did in our last 2. Y equals 4 to the x is the inverse of the log base 4 of x. So let's do this. We'll graph, we'll come up with the points on 4 to the x first. I'll do that in green. Get this out of the way. There we go. So we got -2, -1, 0, 1, 2. We've got 1/4, 1/2. Nope. Goofing up. My base is 4. 4 to the -2 is 1/16. Then it's 1/4, 1/4, 16. Those are the points on 4 to the x. Now, I don't need you to graph the exponential here because our goal is to graph the logarithm. But why did we find those points again? We found those points, okay, because we want the points on y equals the log base 4 of x, the parent curve. So what are my points here? 1/16, -2, 1/4, -1. All right. 1, 0, 4, 1, 16, 2. All right, let's graph those points. Four, 1, 16, 2 is going to be off my graph. That's okay. There we are. All right, so that's the graph of the parent curve. Now that I have the parent curve graphed, now let's do our transformations. Let's see here, what color should I do next? Okay, let's graph in green our first transformation, which we know would be the vertical stretch by 2. So let's multiply every y value by 2. -2 times 2 is -4. -1 times 2 is -1. 0 times 2 is 0. 1 times 2 is 2. So there's my vertical stretch by 2. And lastly, a final graph. Let's move this thing up 1 for the +1 in front. Every green point's going up 1. Notice, did our vertical asymptote change? If we vertically stretch out something, does that change x values? No, it doesn't. Okay. If we move a graph up, does that change x values? No, it doesn't. So the horizontal asymptote's the same. Our domain is the same. Okay. All right, let's graph this one. All right, a few different things going on here. First thing, I don't like this divided by 2. Isn't that the same as 1/2 times The log base 2 of x minus 1. So identify your transformations here first. We know this 1/2 is a vertical compressed by 1/2. We know subtracting 1 from the x is going to move the graph right 1. So I know my transformations. What do I need to figure out? I need to figure out what does my parent curve look like. So if I strip away those transformations, the parent curve is y equals the log base 2 of x. How do I figure out what y equals the log base 2 of x looks like? By looking at its inverse, which is y equals 2 to the x. So let's come up with points on 2 to the x first. See, following the same process every time. What's the parent curve? What's its inverse? All right, there's the points on the inverse. Now let's get the points on the parent curve by switching the x's and y's. Let's graph those. Keep wanting to hit that pause button. That's where my colors usually are. All right. Now that we have that, we see 2 transformations. All right, first transformation. We know we do multiplication first, so we're going to do our vertically compress by 1/2. So I'm going to multiply all the y values by 1/2. There it is. And now let's do it again. Okay. Now we're going to do our last transformation, which is to move it to the right 1. Now remember on our last example that the vertical asymptote didn't move because we didn't do anything to x values. But what are we doing here? We're moving everything right 1. So if we are moving it to the right 1, what's going to move with it? The vertical asymptote. All right? So what I want you to do is I want you to draw that vertical asymptote in if it's not 0. That's going to help you plot these points and draw a much nicer curve. All right, so now we're taking the points in green and we're moving it right 1. There we go. Excellent. Good. So that's how we graph. So we had to remember our properties of inverses. Okay? We use those properties of inverses to help us graph. What's the parent curve? What's its inverse? Get the points on the parent curve by switching the x's and y's on the exponential, then do your transformations. All right, that's a great start to graphing. Thanks for watching. We'll see you later.